So today we are going to continue on the exercise that we were starting the other day on the equation of state of neutron stars, okay? And if we have time, which I guess, yeah, it will be the case, I have prepared some additional questions to discuss what we have learned these days from Laura's lectures. So before going on the exercise, I have prepared some review on neutron stars so we can remember a bit what we learned. Okay. So if we remember the structure of neutron stars, there are some layers. Okay, there is a crust, which is the outer part, and it can be divided in two parts actually. An outer layer, which is basically a form of neutron-rich nuclei. And if we go a bit farther inside the crust, then we go into the inner layer in which neutrons have started to drip from the nuclei, and there is a neutron gas coexisting with the nuclei. And if we go farther inside, then we go into the core where there are no more nuclei. It's just a soup of neutrons, but not only neutrons, it's mainly neutrons as we saw, but there are also a small amount of protons and also the same amount of electrons to keep charge neutrality. And then if we go to higher densities, then we might have hyperons, and as we saw, we can also have kaons, as we will see this afternoon on Laura's lecture. And we also in the exercise today, we will see what happens if we can have kaons inside neutron stars. And also strange phases like quark matter and other things, okay? So in order to determine the composition of the neutron star matter, we saw that, for example, in the case that we consider that we are in the outer crust and we have a matter composed of neutrons, protons, and electrons, then in order to determine the composition, the fractions of each of these components, we saw that we need to impose some restrictions. One of these is the equilibrium against weak interaction processes. This is what we call beta stability. And this gives us the relation between the chemical potentials, right? And also we have to impose charge neutrality. Okay, this gives us the relation between the proton and the electron densities. And if we also impose baryon, the conservation of baryon number, then we have that the sum of the neutron and proton densities has to be the total baryonic density, okay? But to reach these equations, we can use another way, and we can reach the same equations by minimizing the energy density of the system, okay? For example, if we have a parameterization at the one we were given in the exercise, okay, we can minimize this energy density, imposing some conditions, okay, and these conditions, which are them, this is the conservation of baryonic charge and electric charge, okay? So in the case that we have neutrons, protons, and electrons, they read like these restrictions. And then if we use the Lagrange's multiplier method, and remember that the chemical potentials are defined as the derivative of the energy density with respect to the partial density. Then if we take the derivatives on this function here, we see that the derivative of this with respect to the neutron density, this gives the derivative of the energy density with respect to the neutron density. This is the neutron chemical potential minus alpha. So alpha has to be the neutron chemical potential. Then if we take the derivative with respect of the proton density, we get that beta plus the proton chemical potential has to be the neutron chemical potential. And the derivative with respect of the electron density, this gives us that beta has to be the electron chemical potential. So we get these same relations that we had for the chemical potentials from beta stability. Okay, and we also have to take the derivatives with respect to alpha and beta, okay, and this gives the restrictions that we were imposing, so conservation of baryonic charge and the conservation of electric charge, okay. So this is in the case that we have matter composed of only neutrons, protons, and electrons. So my question now is, can we have muons? And the mass of the muons, I'm telling you that it's 106 MeVs. Okay, so what do you think? So we saw that the chemical potential of the electron, okay, sorry, I'm doing this with the mouse and it's a bit complicated, but was given by 3 pi square density of the electron to the 1/3. Okay, let's calculate this value at saturation density, okay, rho 0 equal to 0.16 Fermis to the -3. Okay, and a proton fraction, let's say, of the order of 0.05. Okay, so this electron density is the same as the proton density, which is the proton fraction times the saturation density. What value do you get for this chemical potential? Try to do this simple calculation and tell me what you get. Remember that the HC was 197 more or less MeVs times Fermi for the conversion of the units. Does anyone get the value? Can anyone tell me something at least? So I know if you are doing the calculation or not.
I don't know whether they can read well your writing.
Okay, I'm saying that I want to calculate the electron chemical potential, okay, this mu E at saturation density. Okay, so this is 3 pi squared times the electron density to the 1/3. Okay, and this electron density, we saw that by conservation of charge, electrical charge has to be proton density, and proton density is the proton chemical potential times the baryonic density, which we take saturation density, so 0.16 Fermis to the -3. And for the proton fraction, let's say we take a small value, it has to be small, okay, in neutron stars, so we take 0.05 more or less. And we will need to change the units to MeV. So remember that H bar C is 197 MeVs per Fermi. So if you do this calculation, you will see that the electron chemical potential is at saturation density around 120 MeVs. So this is higher than the mass of the muon. So we will expect that we have muons already at these densities, okay? Because the electrical chemical potential of the electron is the chemical potential of the electron is larger than the mass of the muon. So it is energetically favorable for these electrons to decay into muons, okay? Because they are very high in their Fermi C. So yes, from a certain density onwards, yes, we expect to have muons in neutron stars. Okay, so this is what I was asking you to do that, okay? Okay, so what I'm telling, okay, if we plot the occupation of the Fermi seas of each of the species that we have, what we see is that when we increase the neutron, when we have more neutrons, they can decay into protons and electrons, right? Because of beta stability, and they increase these proton and electron seas. And we see that at some point, this should be the muon. If we reach the mass of the muon at some point, it will be also possible that this muon Fermi sea is also occupied. Okay, so at some point, our matter will not only be form of neutrons, protons, and electrons, but neutrons, protons, electrons, and muons. Okay. So, and this onset for the appearance of muons in neutron star matter can be determined by the Lagrange minimization procedure that we were using. But now consider that we also can have muons. If we do that now, okay, now this function depends on also on the density of the muons, okay? And the constrictions that we have to put are the conservation of baryonic density, which is the same, but for the conservation of electrical charge, now we have that the proton density has to be equal to the sum of the densities of electrons and muons, okay? And if we do that, we get the equations that will give us the composition of the neutron star, okay, of the neutron star matter. And these are the relations that we get for the chemical potentials. Okay, we have the neutron chemical potential from the decay to protons and electrons has to have this from here, but now also the at any density, the chemical potential of the muon has to be equal to the electron chemical potential, and the conservation of the baryonic density and the electrical charge give us also these relations for the densities. Okay. So let's go back to the exercise. Okay, we had this parameterization for the energy per particle of the system. Okay. In terms of the proton chemical, the proton fraction and the density of the system, the baryonic density of the system. Okay. So what we want to do now is to consider that neutron star matter in beta equilibrium is constituted by neutrons, protons, electrons, but also muons. And to taking into account that the chemical potential of the muons is given by the Fermi energy. So it is the mass, the square root of the mass of the muon squared plus the Fermi momentum of the muon squared. Okay, for the case of the electrons, the mass could be neglected. Okay, but for the muons, we have to take the full Fermi energy. And we have the mass of the muons, which is 106 MeV. And we have to calculate the density at which muons will appear, that we have seen that has to be around saturation density, and then plot the chemical potentials and the fractions for each of the species as a function of the density, okay? Let's do it first in the case without muons, so we will see the difference that we get once we include the muons. In this case, we have the beta stability and the conservation of baryon number and electrical charge, giving us these relations that we have seen already many times. And the other day, we saw that from the parameterization of the nucleonic energy per particle, we could calculate this difference between the neutron and the proton chemical potentials. Okay, we had this easy form here. And for the chemical potentials of the electrons, as I have just said, we took this Fermi electron Fermi momentum. Okay, so this is 3 pi squared density of the electron to the 1/3. Okay, and this has to be equal to this value here, as we did the other day, and we define this function here in terms of the density and the proton fraction that we had to solve this equation, setting it equal to 0 in order to calculate the proton fraction for each value of the density. And we could plot this proton fraction, okay? And also, we could also calculate the neutron fraction and the electron fraction, okay? From the conservation of baryonic density, we have that the neutron fraction has to be equal to 1 minus the proton fraction, and the electron fraction has to be equal to the proton fraction at all densities to ensure charge neutrality. And we can also calculate the chemical potentials. We derived the expressions for the neutron and proton chemical potentials, and we saw that they have to take this form here in terms of all the parameters that we know. And the electron chemical potential, we just saw that it takes this from here. So we can plot these things and see how they look like. And if we do that, we see, we have these plots here, okay? So as we said, the chemical potential of the electrons, which is this line here, at around saturation density reaches 100 MeVs, and this is the mass of the muons. So we expect that when we include muons in our equations, we will have muons appearing around here, okay? And this is possible because, as I said, for an electron in the top of its Fermi sea, it is energetically more favorable to decay into muon through this weak decay process, okay? So we see that we need to include muons. So let's do it. In this case, beta stability gives us the relations for the chemical potentials, okay? So we have this additional one, the electron chemical potential has to be equal to the muon chemical potential. And the charge of baryon number reads the same, but for the electric charge, now we have that the proton density has to be equal to the sum of the electron and the muon densities. And for the muon chemical potential, we take this here. It's a bit more complicated than for the electron, but we can see that we can also derive the muon density in terms of this chemical potential. And here I have included this Heaviside theta function because this density will apply only if the electron chemical potential is larger than the muon mass. Otherwise, we will not have muon, so the density will be 0. So I put this theta here. Okay. And combining now the condition for charge neutrality and the beta equilibrium, we can derive this function here now that it's a bit more complicated than before, but we can still solve it using, for example, Mathematica or numerically or the way you prefer. If you want to do that, I really recommend you to try to code it and see if you really get the same plots as I'm showing you. It's a good exercise to do. And so first of all, we will determine the density at which muons appear just by solving this system of equations, right? For the electrical chemical potential, we know its expression, but we also know that we want to impose that its value, it's the muon mass. And if we do that, we get that the muons should appear at a density of 0.84 times saturation density. And this happens when the proton fraction is 0.04. Okay. So if I do the plots now, okay, I get these things here that are a bit different than before. For the muon chemical potential, we see that it's equal to the mass until the electron chemical potential takes the same value, then both chemical potentials evolve the same way because one of our restrictions is that the electron chemical potential is equal to the muon chemical potential for all densities, and we see this here. Okay, and when we plot the proton the particle fractions, we see that, yeah, the density that we have determined that it's close to saturation density, muons appear, and the proton fraction at each time once muons appear has to be the sum of the electron and the muon chemical potentials. Okay, so any questions up to here? So, okay, let's go to the next exercise. Now the question is, can we have also a condensation of anti-kaons inside neutron stars? And Laura will talk about this this afternoon, and we will see that, yeah, it's one possibility to have that. But okay, we can think about the same reasoning as we did for the muons. Kaons are bosons, so in principle they could appear, and they are, if we consider anti-kaons, so K minus, they will help electrons in compensating the charge of the protons. Okay, so but its mass, it's much larger than that of the muons. This is almost 500 MeV. So in order for the electron chemical potential to reach this value, this is very high, so this might not happen. But we will see this afternoon that when kaons are in matter, they feel attraction. So the chemical potential, because of this attraction, reduces. And the exercise tells us to consider that it reduces this way, decreases as it has at zero density. So in vacuum, it is the kaon mass, but once we put it in medium, its chemical potential decreases linearly with density, with factor A that we take 100 MeVs. And we have to see with this equation if it is possible to have a kaon condensation in neutron stars. Okay, and if so, we have to determine at which density this happens. And we have to draw the two quantities that we need to compare. So which are these quantities? The chemical potentials, basically. We need to compare the electron chemical potential with the kaon chemical potential and see if they cross at some point. And if this happens in the density that is low enough to be reached inside neutron stars, then we will see, this will mean that kaons condensate inside neutron stars, considering that they satisfy this equation for the chemical potential. Okay, and for now we will not consider muons, we'll just consider electrons and the kaons. Okay, so we consider matter composed of neutrons, protons, electrons, and anti-kaons. So the reactions that can take place now to for the chemical equilibrium are these ones here. Okay, the neutron decay into proton and electron, and the neutrino that escapes. But also we can have the decay of the neutron into a proton and a K minus. Okay, this reaction is now also possible if we consider that we have them inside the neutron stars. So we get that the chemical potentials have these relations. Okay, the neutron chemical potential is the sum of the proton and the electron chemical potentials, but also is equal to the sum of the proton and the anti-kaon chemical potential. So it follows this thing that I was saying, no? That once the electron chemical potential is equal to the kaon chemical potential, we will have the saturation. So this is the condition that beta equilibrium imposes to us. Okay, so yeah, exactly, that's what I was saying. And Yeah, and the density will be determined by the point at which this is the quality happens. Okay. So the electron chemical potential is again this form here is the Fermi momentum 3 pi square the proton fraction times the density to the 1/3. And the chemical potential, we just take that it's the mass minus 100 the density, okay? And if we plot these things here, we get these plots, okay? So we see that the crossing happens at around at exactly 2.91 times saturation density. And this is a density that it is rich in neutron stars. So in principle, if this is true for the anti-kaons, we would have to expect that the kaons appear in neutron star. They condensate at this density. Any question?
Yeah, hello.
Yeah.
I wondering why do we choose to have anti-kaon in the neutron star and not a smaller or lighter particle like pion or something like that?
Well, pion condensation has been discussed in the past, and I really don't know much about it, but some people discussed at the beginning that it could happen like some decades ago, but then it was shown that it cannot happen inside neutron stars. I don't remember the reason why, but pion condensation, it's quite complicated to reach in neutron stars. Although there are some models that say maybe yes, but I really don't know much. Maybe you can ask Laura this afternoon. She might be able to give you a better answer. But kaons instead, they are a better possibility, and it's a possibility that people are considering rather than pions. And kaons, anti-kaons in this case, because this field is attraction in the medium. So some people think that they can appear.
Okay.
Okay, so now I have prepared you some additional questions, and yeah, because we have some time, I would really like that you try to think about them and you answer them, okay? So the first question is, what does self-consistency and in coupled channels mean within the Bergner-Hartree-Fock approach for hyperons in nuclear matter? There are two questions here, right? What does self-consistency mean? And what does coupled channels mean? Okay, Laura was talking about this yesterday. Do you remember? Can anyone tell me what this self-consistency means? I give you some minutes. Maybe you can check on the slides from yesterday. Anyone? Even if your answer is not right, we will discuss it why it's not right, or what do you think it means? Just try.
I remember maybe just something.
Yeah.
We were calculating the interaction between all the nucleons, the effective interaction, and
Yeah.
on one end, To calculate it, we need some information, but when we put the interaction inside some expression, we need another information that
Yeah, you're
it's
on
all
the right
connected
path.
like a loop, and this is why it was self-consistency. But I can remember exactly what
Yeah,
they were.
exactly. Yeah, you're right. You remember exactly what you meant, and although the words are not exactly the right ones, but what you are saying, right, is that in the calculation of these effective interactions, you need information on the single particle energies. If you remember the equation, you had to put as an input these single particle energies. But in turn, in order to calculate these single particle energies, you need to know this effective interaction. So it's like two equations that are coupled to each other. So you need to solve them in an iterative process to reach this self-consistency of the results. Until once you put the input and the output is the same as before, then you have reached this self-consistency. Okay. And this is something that you need to impose when you solve this Bruckner-Hartree-Fock theory. And in coupled channels, what does it mean?
Maybe she was talking about processes, two particles in two particles, two hyperons, for example, in one C and one nucleon.
Yeah, so usually you solve your problem in a sector. So for a given isospin number and for a given strangeness, and you have that a given channel. So let's say, for example, lambda nucleon, this channel has the same isospin and strangeness number than, for example, this another channel here, okay, the sigma nucleon. So when you solve the problem for the lambda nucleon, you have to consider that it is coupled to this other channel because they have the same quantum numbers. So this is what coupled channels means, right? That you need to consider all the hyperon nucleon states with the same quantum numbers when you solve your problem. Okay, do you understand it? Do you have any question on that? Okay, if not, let's go to this question. When nucleons and hyperons are present, okay, this is an easy one, no? The equation of state gets softer with respect to the case when only nucleons are present, because adding one particle species and keeping the total number of particles fixed means opening a set of new available low energy states that can be filled, lowering the total energy of the system. Stiffer with respect to blah, 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 the same, because okay, the same reasoning, but because this increases the total energy of the system, so it's stiffer. Or softer with respect to the case when only nucleons are present, because adding one more particle species means reducing the set of already available low energy states that can be filled, lowering the total energy of the system. What is the right reasoning? First, it gets softer or stiffer when hyperons are present?
Softer?
Softer, okay, so B is not the correct one. And it's softer because there is an opening of a new available low energy state, or because it reduces the number of states. We are introducing hyperons, right? So we have more states that are available that can fill their respective Fermi seas. We don't have only the nucleons Fermi sea, but we also have the Fermi seas for the hyperons, so that they are lower in energy than when we don't consider them. And so nucleons go to higher states in their Fermi seas. So the right answer is obviously A. Okay. You understand it, right?
Hello, perhaps I missed this, but what does soft mean?
Soft means that the energy, when you plot your equation of states, so the energy and the pressure with respect to the density, soft, I mean, you have to say soft with respect to another one. So when you compare, there is something that is softer than the other one. So softer means that the energy or the pressure are decrease with respect to another one. So when you put hyperons with respect to the case where you only have nucleons, the equation of state, the energy and the pressure as a function of density reach lower values than when you only include nucleons. So this means softer. And when you solve the TOV equations to calculate the mass radius relations, you get smaller masses for the maximum mass that your equation of state can give for neutron stars. And this is why it's a puzzle, because including hyperons softens the equation of state, and then you cannot reach the two solar masses from experiments, from astronomical observations. Okay. Okay, so this is from yesterday. In the Bruckner-Goldstone theory, the dominant diagrams are those with the more number of whole lines. And for each diagram, each whole line implies an integration over momentum above KF, while each particle line implies an integration up to KF. And for low density systems, small KF, the contribution of whole lines is larger than the contribution of particle lines. Or the dominant diagrams are those with the more number of whole lines again, and because whole lines imply an integration over momentum up to KF, while particles is integration above KF. And or the dominant diagrams are those with the less number of whole lines, and because whole lines implies an integration over momentum up to KF, while particles lines imply an integration above KF. And for low density systems, small KF, the contribution of whole lines is smaller than the contribution of particle lines. What is the right?
The B answer.
B answer?
Yeah, I think.
Okay, so A is false first, because it's saying that whole lines imply integration above KF and particles up to KF. This is wrong, it's the opposite. It's what B is saying, right? Whole lines is integration up to KF. It's below the Fermi sea, while particle lines are integrations above the Fermi sea. And the contribution of the whole lines is larger than the contribution of the particle lines. This part is false, okay? The contribution of the whole lines is smaller than the contribution of particle lines. So the dominant diagrams are those with the less number of whole lines. As we saw yesterday, we were considering the diagrams with the less number of lines going downwards. That was the whole lines. Those were the dominant with respect to the ones that had more whole lines going downwards. So the solution is this C. Okay. And the last question that I have prepared. So in the Bethe-Goldstone equation, that is this equation here that we saw that has a similar form as the Liebman-Schwinger equation, but it has this Pauli operator here. What is the meaning of this Pauli operator? Does anyone to try to give an answer?
I think it has to do with the fact that the nucleons interact also with other nucleons.
Yeah, it has to do with the fact that we are in the medium, right? So nucleons are occupying a Fermi sea, occupying the lowest momentum states up to the Fermi momentum. So, okay. And this Pauli operator takes into account the Pauli principle, right? That the nucleons that are scattering have to have momenta that are not occupied by other nucleons. So these have to be momenta outside the Fermi sea. Okay. So this Bethe-Goldstone equation describes the scattering of the nucleons in presence of other nucleons. This is what you were saying. So you have to take into account that some momentum states are not allowed for this scattering. As in vacuum, you can have any value, but now some are Pauli blocked. So this G matrix represents the effective interactions between these two nucleons in the nuclear medium. So if you have any questions, otherwise this is all and we can have some break before the next lecture.
Ciao.
We stop here?
Yes, okay.
Okay.
So thank you, Gloria. I think this is your last lecture, is that right?
Yeah, well, it's the last day today already, so.
So it was very nice what you did, and I'm sure the student will have more questions maybe in the future.
Yeah, maybe this afternoon to Laura or anytime if
yes,
you
of
want
course,
to contact me by email, I'm
yes.
fine. I'm completely fine with it, okay.
Okay, thank you. So we stop now and we start again exactly at 11 since we will have more than 10 minutes.